So this was put together with Fabien Leclerc, who's now working at the French Hydrographic Service. So what I'll go through on these slides is first to look at how we define the wave field and how we go from the wave properties to the spectrum. The different types of spectra you can have. So either it's a frequency spectrum if you have time series, or a more complex spectrum, which in general would be even in 4 dimensions, because the wave motion is in x, y, z, and then time. So these are 4 dimensions. And then issues with wave linearity or not, and then maybe stationarity too, and what wave spectra typically look like. Right. So the ocean waves we're looking at, typically they are part of a wide family of surface gravity waves, which go all the way from very long waves that would also involve the effect of Earth rotation, the Coriolis force at these very long time scales. For oceanographers, this is short, I know, but for wave people, these are long waves, so essentially the tides. And then in the middle, we have all these waves with a period of a couple minutes to tens of minutes, which are usually generated by wind variations and earthquakes. And if you have a meteorite splashing into the ocean, that will also make some tsunami. But so these are essentially tsunamis and storm surges, which nicely for us don't happen very often, which are of course very important in some regions. If you want to look at extreme events, in some cases the extremes will be actually dominated by tsunamis. It's not the case here on this coast, but I guess it depends on the return period you're looking at. And the stuff we'll be dealing with today is not this stuff. We'll actually look at everything which is generated by the wind, and that would go from very short waves. So at the shorter end of the spectrum, waves that have a period of small fraction of a second, also involve not just the effect of gravity, but also the effect of surface tension. And so this is called capillary waves. We will actually not do much about capillary waves, so I'll just get rid of them now. But these are actually important for defining the roughness of the sea surface, and that can have some feedback effect on the domain waves. So these will be parameterized in what we'll do in terms of modeling these days. And then you have all the stuff which is generated by the wind, and that will depend on the wind speed. And so you have stronger wind with larger fetch, we get bigger waves, and we'll see that. So this is where most of the energy of the waves lie. And there's also this bit here, which is called infragravity waves, which are waves of period typically longer than 25, 30 seconds, so between say 30 and 300 seconds, which are generated by the swell on the shoreline through nonlinear interaction that generates waves going back into the ocean. And this is kind of things that we'll also work with in terms of modeling. And these are typical wavelengths in deep water. So that the stuff we were looking at will go from, let's say, around a meter to 10 seconds is 150 meters. That's a very easy number to remember. Because of the wave dispersion relation, if you double the period, you will multiply the wavelength by 4. So 20 seconds, which is a pretty long swell, would be 600 meters. And sometimes it happens that we actually have swells up to 25 seconds. Last winter in Europe was actually really amazing. So we had this 25-second swell, I think it was January 6th, a really big event. And so then some coastal engineers and people that work on marine energy started to worry, I have to worry about these very long ways into the design of my structures and windmills and what have you. So yeah, so 25 seconds is possible. And beyond that, it really becomes extremely rare. So that's a typical scale of wavelengths and periods you will encounter in the ocean. Of course, if you work in the Mediterranean, it will seldom go beyond 10, 12 seconds. It's about a factor 2 from the large oceans. That's because the fetch is so much restricted in the Mediterranean. And so the way we actually describe the sea state is through spectrum. And this would look a bit like that. So essentially, what the spectrum is the distribution of the wave energy in terms across the frequencies. So it will tell you at which frequency you have some energy, and that will typically what it looks like. So these are just a bunch of spectra. We have some high frequency parts which rolls off. The frequencies are typically it rolls off like f to the power 4 or 5, depends how far you go. Sometimes you have several peaks in there. That's because the short waves are driven by the local wind. It's what we call the wind sea. And then you will have some longer waves, which may be coming from somewhere else, which will be a swell. And then this part here are infragravity waves, and you see this is a log scale. So the energy here, it's 3 dB compared to this. So this is a factor of 1,000 from here to there. And so the energy here is much less than that. In terms of energy, at least in the open ocean. In terms of energy, there's really little. Of course, if you work on the beach, these can be actually more energetic than these ones. So on the beach, these actually are very important. And this is why people that work on sediment transport are actually usually include infragravity waves. All right, so the wave motion happens in all 4 dimensions. And before I go to details, I'll just review how I some notation here. So in all I have, the bottom will be at d equals minus h, and that h is a function of space, so it's a function of x and y. And here, of course, I'm always have a bottom with a single value definition. That you don't have a cave under the rock that waves go through it. Some people actually are studying that. If you have a plate, what's happening, below the plate and stuff like that. But here we'll just think that the bottom is just one single value function, z as a function of x and y, or longitude and latitude on the Earth. Then you have a reference level z equals 0, which is arbitrary, and that's what people call the datum. And you have to be careful a bit about that, because there's many different definitions of the 0, right? So people that do charts, they have the 0 of the nautical charts, which is not the mean sea level, and which can be different in definition from one country to another. So in the US, they use a mean low water, or the lowest low water of the, because they usually have a tide with, especially on the West Coast, the tide with 2 lows every day, but they don't have the same low value. So one low tide is lower than the other low tide, so they take the minimum of the 2, all right? Here in France, you tend to take the lowest astronomical tide, and there's actually a shift of tens of centimeters below that. So always, when you do coastal work, always be careful about the datum definition. In the open ocean, you typically don't care because this is a shift of like 1 meter or 2 maximum. And so compared to 100 meter depth, maybe it's not a big deal. But as soon as you're going to the coast, then the datum definition is fairly important. So yeah, make sure you know what your 0 is and work with that in a consistent way. In terms of modeling, what we usually do is we actually put our depth definition compared to the mean sea level, so that during the computation we will have a change in mean sea level. So zeta would be my surface elevation, and the mean sea level is zeta bar, and that's the mean over, say, half an hour. That's the shorter time scale compared to the tide. And so the total mean water depth will be h, so the distance between 0 and the bottom, and this plus mean sea level. So here zeta bar is negative, so that's capital D is actually less than h. All right. These are small technicalities, but they will be important at some point. So what's really important for the waves, they don't care about what the arbitrary datum is. The waves only care about the physical depths, which is a d. All right. So wave motion happens in all 4 dimensions, in space and time. But waves have a very nice property of being very close to irrotational. And of course, there's a bit of vorticity with currents and the boundary layers, but we'll just forget about it for now. So let's say for now it's irrotational motion, which means that it's a solution. You can define a velocity potential, which is a solution to Laplace's equation. And what happens is that this condition of irrotationality actually removes one dimension from the problem, because actually you can reduce everything to something which is 3 dimensions. So that's how we go from 4 to 3 dimensions. And for example, this means that the vertical dimension, the vertical dependence of the motion is dictated by the horizontal variation. And this is just a property of the Laplace equation. If you plug a cosine wave into the Laplace equation, that will automatically give you something which behaves exponential kz. And this is true for nonlinear waves. This is true for everything which is irrotational. It's the same thing with electromagnetic waves in a waveguide. Laplace equation gives you that. Of course, if you don't have something which is exactly cosine is horizontal, you get something different on the vertical. And so if you have something that changes in space, you'll have something a bit different from that. But in general, it's a very good approximation. So in deep water, we'll have exponential of kz, and because we have in intermediate shallow water, you can actually have a plus k and minus kz, and so if you do a sum of these two, you can write that as a hyperbolic cosine. And because you want to satisfy the bottom boundary condition, that typically you write that as a cosine, hyperbolic cosine of k times d plus h, which this d plus h is 0 at the bottom, because this is how I define my bottom, that's equal minus h. But the cosine, hyperbolic cosine will be equal to 1, and the derivative of it is equal to 0. So the vertical velocity with that on the bottom will be 0. That's for the motion in water. There is also, of course, motion in the air. And people that worry about how waves are generated by the wind also are worried about what's happening in the air. And also, it's an issue for swell dissipation on long scale, how much friction you have between the air motion and the water motion below the waves. And actually, in the air, you also have a motion which decays exponentially up, exponential minus kz. And in all my stuff, z is positive towards contact. So my z is positive going up, right? So that would be what it looked like in deep water. So here you have a plot of the velocity field. No, the pressure, yeah, the colors is the pressure anomaly. So the deviation from hydrostatic pressure due to the waves. And that's for a second wave propagating in deep water. So it goes like, these are something like fraction of the period. So the wave pattern travels from left to right, and the arrows here are the velocities. And you can see here that here in deep water, the velocities are along the isopressures, and this is because you have a balance between the pressure gradient and the centrifugal acceleration. So essentially, the water particles go around, and they're in balance between the acceleration and the pressure gradient. That's what happens. That's true only for deep water. All right. So the important thing to note was, this 3-dimension thing. So we know in advance what is a vertical decay. It's also true for nonlinear waves, and also true also for if you include the water compressibility into the problem. But the only time when it's not exact is if you look at the effect of sheared winds or currents, because then you introduce vorticity, and so you don't have the Laplace equation anymore. Then you have to go to a Rayleigh equation for solving the wave motion. Okay, so we're down to 3 dimensions, and now we'll go down again to 2 dimensions only in terms of the wave properties. And this reduction to 2 dimensions is made possible by the fact that waves are really linear. And the good proof of that is actually observe the wave motion and measure it and make a spectrum of it. You will see that the energy is not anywhere. And so this is our examples of, it looks a bit funny, but these are wave number spectra, kx, ky, so the 2 components of the wave number, taken at different frequencies. So from 0.7 hertz here all the way to 1.6 hertz. And this is coming from a stereo video system. So we actually have a movie of the surface evolving in time. So we have the 3-dimensional data. So we have our elevation as a function of x, y, and time. And to make a Fourier transform of this x, y, and time, you get kx, ky, and frequency. So we have this cube of Fourier transform, and you make slices through this cube. And you will see that here, it's a log scale. So most of the energy is where it's red, and it's along these curves here. So the circle, the dot dashed circle here will be the dispersion relation from linear waves, which is omega squared equal dk times the tangent, hyperbolic tangent of kd. So in deep water, it's omega squared equal dk. All right, and so we verify that actually the data is actually around the dispersion relation. At higher frequency, you start to see a bit of things inside of the dispersion relation. So now it becomes bigger here in red, and these are actually the nonlinear part of the waves. But if you only look at up to 1.2 hertz, up to here, most of the energy is actually linear along the linear dispersion relation, and then this stuff is actually the harmonics. So it's 2 times the frequency and 2 times the wave number of this guy here. So there is a bit of nonlinearity that you can find if you have this kind of data, but for most purposes, we will actually neglect this and we'll say, okay, well, most of the energy is along the dispersion relation, so we'll just assume that's correct. What you can also do is to transform the wave motion equation to associate actually the bound waves to the free waves, and maybe I'll get into that later. But yeah, so just bear in mind that there is some nonlinearity at some point, which causes some deviation from the dispersion relation. But for most practical applications, it will be negligible because this happens only at high frequencies, and these are essentially the harmonics of the dominant waves. In shallow water, it becomes stronger, and so you have to worry a bit more about it. But yeah, so we'll get back to it. So we went from 4 to 2 dimensions, thanks to rotationality and linear property of the waves. And so in most applications, it's enough to describe the T-state with this 2-dimensional spectrum only in frequency and direction, or wave number in X and Y. And this is enough to describe what you have. In most cases, this is essentially when the linear waves, the order solution of the wave equation, dominate. And that happens typically near the surface and at around the peak frequency. If you're not working near the surface and not around the peak frequency, you have to be a bit careful. And it's just a warning about that. This is an example of a pressure record taken from a tide gauge, which in 100-meter depth just offshore of here. And what you have here is a frequency spectrum. So we have frequency here on this axis as a function of time. So this was a 2-week experiment. And again, this is a log scale. So you have most of the energy in red is here. But you can see that at higher frequencies, you have some blue, yellow stuff here. And these are actually nonlinear pressure contributions, which actually are bigger than the linear part when you are working in deep water. This is one of the reasons why it's very difficult to measure waves in deep water with a pressure record at the bottom of the ocean. If you actually are very clever, you can actually find a way to use this data and combine it with that to get some information about directional properties. This is what Charles actually is working on. So sometimes this high-frequency nonlinear stuff can be useful, but for most people it is a nuisance because essentially it's hiding the linear part that maybe you wanted to use to measure the high-frequency waves. All right, so there's some nonlinear stuff, but we'll just forget it for now, and we'll work from spectrum in 2 dimensions. So now we'll go to the most simple spectrum you can think of, which is what happens when you have some time series. So you measure a property in time, a function of time. So that could be the pressure at the bottom of the ocean, that could be the surface elevation, that could be the acceleration, the velocities. All these things are related to one another. And here's an example here at the top, coming from a pressure record on the cliff, just some small island of Florida here. So if you look at the pressure record for here 20 days, it's not a surprise. What you see mostly is the tide, all right? And if you make a spectrum of that, so essentially if you take a Fourier transform and look at the amplitudes of the components, you will find this kind of distribution which has discrete lines in your spectrum. So you have well-known and well-defined frequencies at which there is some energy, and this corresponds to the forcing by the moon and the sun and some other funny things. And so the dominant peaks here at some 12, this is at 12 hours and then 12.3 hours. This is what is known as the S2 and M2 tides, all right? So the dominant tides here in west of France. But if you take a small bit of this data set and blow up only for like 30 minutes, and actually it's only 400 seconds, and if you look at the pressure measurements for these 400 seconds, you see it's going to go up and down, up and down. And it's much less regular than this curve here. So you could try to approximate this by the sum of a few components. Like, for example, if you just take one sinusoidal and then make a sum of 2 or sum of 3, it will never look exactly like this. And this is because the phases of the waves are random. It's not like the tides where the phases are every time the same. So we have random phases. And also we have energy not at discrete frequencies, but at all frequencies. So if you make a spectrum, it will look something like that. Instead of having some discrete lines, it will look like this. And so instead of actually doing an amplitude spectrum, the problem is if you do an amplitude spectrum, the amplitudes you will find will be a function of the length of the record and a function of the time resolution you use. So in order to have always the same amplitudes, we normalize these amplitudes by taking them squared. So we take the FFT squared and we normalize it in such a way that we that the area here in black, so the area below the curve of the spectrum, will be the variance. So the sum of that area, all this black thing, is the variance of the signal. This is how you typically normalize the spectrum. So the sum of E of f, so my spectral density here is the E of f times f, which is my spectral increment. So EF is my resolution and frequency. The sum of that is equal to E, and E is my variance of the T-surface elevation. In other words, this is the average of Z minus zeta bar squared. Right, that's the variance of the T-surface elevation. And the nice thing is that you can, so all we will do with waves, instead of working with amplitudes, we'll work with variance. And so you have to be careful about that when you transform data. When you take an average of the wave height, it makes no sense to take the average of the wave heights, but you want to take the average of the wave height squared and then take the square root, because what is conserved is really the variance. And in physically, this variance of the T-surface elevation is almost the energy. Yes, I have something like that. Yeah, it's almost the energy, and I will call it energy, although the units of that are meters squared, and the proper energy is actually the water density times the gravity times this variance. So rho dE, that will be in joules per meter squared, right? So this is what should be real energy. But because it's kind of cumbersome to carry around this factor rho g, which is only a factor 10,000, we'll just call this E energy. That's improper word, but this is what people do usually. And yeah. So we have this variance, wave energy, and essentially what the spectrum is telling us is how this variance is distributed across the frequencies. That's a spectrum. The spectrum is only that, nothing else. And what I want to show here is that it's very different to work from something which has a random phase in amplitude and something which has deterministic. And so this is why people that work on tides work with amplitudes, but we work more with the energy or the variance and how it's distributed across frequencies. Okay. Now the nice thing about the spectrum and this variance is that if you have a Gaussian T-state, if it's random, then you can actually get all the statistics of the T-surface expressed as a function of the spectrum. So the mean height, the distribution of the periods and everything, they are all given by the spectrum. Now, you may know, and some of you are actually working on extreme T's, and people have been working on freak waves and kind of stuff. It's more fun because it's not exactly Gaussian, and so then you may want to have some corrections. But actually, there's a very nice paper by Aziz Taifoun, who showed that if you want to, even have the full distribution of wave heights, including freak waves, you just make a small correction to linear wave theory by going to second order, and that gives you a very nice fit to the full distribution. So the full wave statistics are actually very well closely given by the spectrum, Gaussian T's, and possibly going to some corrections. For the slopes of the sea surface, which is important for remote sensing, it's a bit the same story. It's a bit more complicated. We can talk about that if you're interested. Okay, so we have this 1D spectrum. So make time series, take the Fourier transform, square, divide by delta f, and we get this. But of course, as I was telling you, a 1D spectrum is not the full distribution of the T-state because it doesn't tell you where the waves are coming from, essentially. And this is what we want to work with the 2D spectrum. Right. ideally, to measure the 2D spectrum, you want to have measurements everywhere in space, and do a Fourier transform in X and Y. And this is what we can do with stereo video systems these days. Or if you had like many gauges and sensors, you could have an array of these and make a Fourier transform of that in space. So we're having a lot of fun with stereo video cameras. Typically, so when we do that, we can reduce this. So we have the 3D data, we take a 3D spectrum, and you can compress that in 2 dimensions because waves are essentially linear. And then you will have some frequency direction spectrum. That's an example. I'll go into the details how that derives. We have the energy now, the function of frequency and direction. And the sum of that over the directions and over the frequencies is, again, our variance of the surface. All right, so the spectra is very simple. When you sum it, you should get back the variance. That's in 3 directions. If you have some spatial data, you will alternate. Maybe you will want to work rather with a wave number in X and Y. So Kx and Ky will be the 2 components of the wave number vector. And this is actually what numerical wave model will compute is at each point of the grid, you'll have some spectrum, which is something like that, and you will compute how it evolves in space and time. Right, the issue is how to actually measure the spectrum. And this is not easy because most data is not a video system or a crazy array, but it's a buoy or a pressure velocity system, what people call PUV. So with a single buoy, what you have is essentially 3 time series of, well, the buoy usually measures acceleration or heave, speed, and roll, but you can convert that back to X, Y, and Z displacement of the buoy. So that's an example from short record here. So you have the X in red, the Y in blue, and the Z in black. What you can see from this record is that they kind of follow one another. You can see that the X is actually maximum after the Z, and this is essentially because the waves are traveling towards positive X. You imagine the water particle going around like that. So first it's going up, and then it's going forward. And this is what happens. If the waves were going the other way like this, then the red curve will be shifted the other way. So anyway, we have 3 time series, so we can make 3 spectra. Okay. But we can also compute the co-spectra. So the co-spectrum is the same thing as the spectrum, but instead of taking the time series squared, you take 1 time series, Fourier transform, then the Fourier transform for another time series. It takes a complex conjugate to multiply these 2. That's a co-spectrum. And so with the combination you can have with 3 time series is 3 spectra and 3 co-spectra. So ideally you have 6 information for each frequency. And from 6 information, it turns out that actually one of these is redundant. So people call it a check factor. And that's essentially the ratio between the vertical and horizontal displacement. And that's only a function of the water depth. And this is, as you may know, is because the water particle motion is deep water is mostly a circle. In shallow water, it's going to be an ellipse squished on the vertical. And so the ratio of the vertical to horizontal displacement is only a function of frequency and water depth. That tells you nothing about the direction. So you're left with only 5 parameters to estimate the directional distribution. And so these 5, you can have different notation from that. So usually here we work with so we have our frequency spectrum, the heave spectrum, the same 1D spectrum we had before. You can define a mean direction, a directional spreading. These are from the first moments of the directional spectrum. You can go to second moments and they get also mean direction and spread from the second moments. Anyway, you end up these 5 numbers. And then to go from 5 numbers to a function of direction, which goes all around the circle, then you have to invent things. So a buoy doesn't measure a directional spectrum. It measures only 5 moments, and then you have to invent the directional distribution from that. So there's many methods for inventing things using fancy statistical assumptions. So that's a maximum likelihood methods, the maximum entropy methods. There's some different flavors of the maximum entropy methods. And these will give you, from only these 5 things, that will give you the full spectrum, which is that. This is what I did from a buoy data. I computed using the MEM, the maximum entropy method, this spectrum here. The reason why I use MEM is, again, taste. and I'm used to it, and I had a code to do it. It's kind of nice. There's some people that say, well, MEM2 is probably better, and I believe them, but I just was too lazy to switch over to MEM2. But definitely MLM is not very good, because MLM will actually bias the directional spreading. So for example, if you compute the spectrum from the moments using MLM, and then if you recompute the moments from the spectrum, you don't go back on your feet to the original moments. And so you get a spreading which is too large, so that tends to smear around. So I don't like MLM because of that. And anyway, when I work with buoy data, I very seldom compare the buoy spectrum to the model outputs. I usually go back to the moments because I want to compare what the buoy actually measures to what the model can give. So what I do is actually I take my wave model spectrum and I compute these things, the mean direction and the spread, and this is what I will compare against the buoy, not the full directional spectrum itself. Of course, it's kind of nice to make a plot to get a feeling for where the waves are coming from, to get like 2 peaks or not. But you're a bit fooling yourself when you're doing that, because you're really you have to invent the details of the spectrum through these methods. So the directional spectrum is not easy to measure. That's one thing. But the reason why we're working with directional spectrum is that, as I was telling you, with a 2D spectrum, you actually have the full statistics of the sea surface if you assume that the waves are linear and rotational. And so you can use this directional spectrum to estimate many other things. So this is the spectrum of the surface elevation, but from elevation you can go to velocities, slopes, pressure in the water, whatever you have. And the idea is that basically, if you had only one wave train with surface elevation zeta, so say for example zeta is A times cosine of the phase, and then you have some quantity A, which is some function m times zeta, so we call m this transfer function. And this is one example, for example, the orbital velocities in the water are this amplitude times this transfer function times the cosine of the phase. Okay, so this thing here would be my m. Then you can compute the spectrum of your quantity A, so for example, the spectrum of u, the velocities, you can compute it as just the spectrum of the sea surface elevation times this transfer function squared. So the transfer function is something very nice. And so this is just to show you that the spectrum of the waves is not just about the elevation, it's really the spectrum of the full motion of the waves, and then you can go from the surface elevation to the velocities or the pressure here, for example. And yeah, one thing here, so this is the dispersion relation. So if you don't have any currents, the sigma here, which goes in there, is even like that. So sigma squared is gk times current of kd, where d is the mean water depth. All right. And of course, when you're doing measurements, it's actually very difficult to measure the elevation. So most of the time, you actually measure the acceleration, the pressure, the velocity. So usually you do that in reverse. So you actually invert this relationship to go from your measurement to the actual wave spectrum. Okay. I just have to make a warning here, is that this was true without currents. And I did my PhD in California, so with a bit of coastal currents and a bit of tide, but I could just ignore that. And moving here, you have to do something about the currents. But maybe we'll do it this week when the tide picks up. I don't know what's the coefficient for the tide this week, but if waves come against the current here, you will see the currents do something to the waves. And one thing they do is actually they change the dispersion relation for the wave frequency omega. Is actually the frequency I had before, so without the current, so that's in the frame of reference moving with the current, plus a Doppler shift term, which is k dot u, and these are vectors. So this is wave vector k dot product with the current vector u. And typically in WaveWatch, we will be solving the wave spectrum, but the wave spectrum will be in a frequency f with the relative frequency. So fr corresponds to sigma. So sigma is 2 pi divided by fr. But if you're working with a buoy or with a pressure gauge, you're actually measuring the frequency, which is this one. So if you work in an area with strong currents, or you're working at high frequencies, you really have to be careful about this. That's the what we work in the model, because it makes life simple, is we actually work with a relative frequency. And so if you want to compare with measurements, you may want to make sure you make this shift back to the real world in which you have this Doppler shift. And this is where the fun begins. It's actually easy to do that in the model because we have the full frequency direction spectrum. If you only have a time series with a pressure record, it's impossible to go from this frequency spectrum here to that one because you don't know the direction of the wave. So it's better to process the wave model output to look like your measurements rather than the other way around. Okay, so this is just one example, for example, of measurements of directional wave spectrum starting from pressure and velocities at the bottom. So the same thing as with the surface buoy, we have time series of P, U, and V. So we have 3 spectra, 3 co-spectra, so it's the same routine. So you can have 5 parameters at each frequency which are independent, and that give you some directional information. And it is essentially the spectrum of the T-surface elevation. So the blue is estimated from the pressure. The dashed here is estimated from the velocities. And if you combine these two, you get a directional spectrum here with the energy in different directions. And again, that was using the MEM method for going from the moment to the directional spectrum. Now, of course, there are some other ways to do measurements, and we will not be working with these data here, but there's this week, but there's a lot of people that have been working here on this thing, and it's actually making observations with the radar that will give you a snapshot of the T-surface. And this is, for example, what's done by radar. So you make an image of the surface, and you can see the waves on top of that. So if you compute the spectrum in X and Y, you actually have the directional spectrum directly, Kx and Ky, and that was done, since the ERS days. There's a wave mode on ERS that was carried over to NVSat and now to Sentinel-1. Sentinel-1 was launched last March or April. Yes, soon I have to update these slides. It's now been declared operational since about a month ago, and so the routine swell measurements we've been looking at on the global scale are actually coming back again live. And there's another satellite which can be launched soon, also making some directional wave spectrum, which is called CFOSat, the China-France Ocean Satellite, that would use not strategic aperture radar, but a real aperture radar. And the launch date is scheduled for 2018, so it's only 4 years from now. And so this is what a SAR image looks like in coastal area. So that's actually close to Le Mont Saint-Michel is around here, and Saint-Malo is here, and that's the Cancale area. So you see the stripes here, the white and black stripes. These are actually correspond to wave crests you can see in the image. It's not really a picture because the surface is moving, so there's some technicalities associated how you go from the real sea surface to actually making a picture. But in terms of spectra, there's a relationship between the spectrum of the image and the spectrum of the waves. And these are, for example, some validation of SAR-derived spectra and the buoy spectrum. I think the buoy is somewhere around here. These are the Santa Catalina Islands in the South California Bight. So this works very nicely when you have swell and it's long enough. When you have some wind seas, it's a bit more complicated because wind sea is introducing some smearing in the image, and for example, in the Mediterranean, it's actually very hard to have a SAR image I give you anyway. So this works really nicely for swells, typically 10 or 12 seconds and longer. But it's not so much for the short waves, not just because of the resolution of the image, but also because of the velocities at the sea surface. And so what else? Oh yeah, so I still have a few more things going back to, so maybe you have some questions before I move on to something else. So spectra in 1D and 2D, other things. So I hope it was clear. It was a bit fast, but So yeah, going back to these 3-dimensional things instead of 2, and the linear or nonlinear aspects. So what I was showing you with the video data is that we can actually see in the spectrum, when you have a 3D spectrum, you can actually see that some energy is not on the linear dispersion relation, but corresponds to harmonics of the dominant waves. And this also is becomes fairly important in shallow water. And there's the question is how we should deal about that. If we only have a 2D spectrum, how we represent this part of the wave spectrum, which should not be linear, related to the linear dispersion. So one way to do that, and it's what has been implemented in WaveWatch, is that as long as if you're working in condition with a flat bottom and it's homogeneous in space, then there's a relationship between the first harmonics, so which correspond to second order waves, and so here in the spectrum you can see here they have the spectrum here and they have a peak here, and so this same kind of example. So you have a spectrum here and you have this peak here, which corresponds to the full spectrum here, including the nonlinearities. So you can actually transform your wave amplitudes to a world in which this second order wave, the second peak, disappears. And this magic transformation is called the canonical transformation. So essentially it will remove that and put the energy back at the peak. So essentially it will put the energy of the harmonics back at the peak, and so it will make this energy travel with the waves. So this is what we would like to do in the model, because these waves are bound waves, so they travel with their longer, so the harmonics are traveling with the wave itself. So the most simple example is you have a Stokes wave, so it's not sinusoidal, which has like slightly pointing sharp crest. But these short waves that are traveling with the long waves, so they shouldn't travel with their own velocity. So you just want to put the energy back so that the model propagates the energy at the same velocities. And then when you're finished with the model, you can post-process the model result to put back this energy where it belongs in frequency. So if you want to compare with the wave gauge, we have a frequency spectrum, then you go back to the world, so you do the inverse canonical transformation to put back this energy at the proper frequencies. And that will take care of a lot of the issues you may have in comparing model with observations in shallow water, as long as these, flat homogeneous conditions. Of course, what you really have in shallow water, so this actually is a measured spectrum. It's not so shallow. I think it's 3-5 meter depth, and these are not very big waves. So here, it seems that it's doing a good job of reproducing this peak here. One thing which we have all the phase average models have a hard time doing is actually to represent what's happening when you have a sloping bottom, because in that case, this energy of the energy of the harmonics the harmonics actually can become free and travel with their own linear dispersion relationship. So the fact that you have these harmonics and they go over a bumpy bottom, at some point these short waves will just get away from the long waves and not will be locked in phase anymore. And this is what we call the triad wave interactions. Is one way to present it. So you can do a modeling for the triad wave interactions if you have the phases or the bispectrum, which is statistical information about the relative phases of the different components. But if you don't have that information, essentially there's no way you can do it. So there's parameterization that works more or less well. Since the default is to use the Aldeburgh parameterization for that, but it will fail miserably if you put like a 2-peak spectrum or something a bit more fancy. So there's But at least the post-processing I can do in WaveWatch is done. That's one of the options. It was essentially work done as MWF in WAM by P.T. Hansen. So we just adapted the module from P.T. Hansen to work in WaveWatch to do that. So you can post-process your spectrum to do the correction for the second order. So that's all I had about. Yes, so it's actually you need a 2D spectrum. So here I showed the result in 1D, but we actually have the 2D information. And also you can use the same piece of code also to look at the EM bias for the altimeter, because it's related to some of these things. So We discussed that with Bertrand. We didn't really go that far, but yeah. So essentially, we're computing the corrections from random waves at second order, so the full second order spectrum, which includes both the quadratic terms, the amplitude squared of second order, and also what's called the quasi-linear term, which is negative, which corrects. If you, yeah, we can talk about that. So now, just a few words about the typical shapes of the wave spectrum, and then I'll stop. So this is, what people observe is that if you have a homogeneous wind blowing from the shore, and if you go look at the wave development from the shore to the open ocean, you'll see the different spectra. So the numbers here are the fetch, so 10 kilometers from the shore, 20, 30, and so forth. This is a classical figure from Hasselmann et al. 1933, which is known as the John Swap spectrum. You can see that the peak moves to lower frequencies, and the energy gets bigger as the wave develop. The other feature here is that you can see that if you look at one frequency, the peak will go high, and then the energy will go down. So this is what people have called the overshoot effect, that the peak is actually higher, or rather the spectrum is actually higher when it is at the peak compared to later on when it's more developed. And this is another example. So here you have the WINSEE peak here, and the fetch again from 4 to 100 kilometers. And this peak here is swell going against the WINSEE. So this is from the US East Coast. It's a log scale, but it's essentially the same thing as this. One funny thing we found is that at very short fetch, 4 kilometers here, you have two peaks. So you have a WINSEE here, and you also have another WINSEE here. And funnily enough, they don't have the same direction. And that's the case in which the wind is not perpendicular to the shore. So here we have 20 degrees between the shoreline and the direction of the wind. So 20 degrees from the normal. And because of that, we have there's a wind component along the shore, which is making the wave grow, and this is actually making this peak here. So this peak here is in a longshore direction, and this one is in downwind direction. So this is a typical thing that you find actually even in the John Swap data. When you look at short fetch with a slightly oblique angle, you tend to have a funny WINSEE with two peaks. So people have parameterized this spectrum like that. So typically you have a Pearson-Moskowitz shape of the spectrum, which corresponds to a fully developed spectrum. And then you put a peak on top of it, so it's gamma with exponential. And so what people have found is that if you take the spectrum and you multiply it by f to the power 4, okay, you will see something like that. So you have the peak of the spectrum here, and because you multiply by f to the power 4, you're just bringing up the tail of the spectrum. So there's a region above the peak, maybe up to 2 times the peak frequency, in which the spectrum times f to the power 4 is flat, which means that the spectrum decreases like f to the power -4. And then at some point, it goes to a steeper decrease, which is f to the power 5. And if you actually want to go even higher frequencies, it will even go faster than that, maybe f to the power 6 or more. This is what we typically find. And in terms of directions, measured spectra actually look like that if the wind is steady. So that's in the energy as a function of the frequency and direction. So it's normalized by the peak frequency, the maximum, then it's at 1. So the peak is here. And as you go to our higher frequencies, the spectrum actually splits in two. And we have what we call a bimodal system, in which we have two peaks in 2 different directions. And these 2 directions, they go away from the wind. So in the wind direction, you actually generally have a minimum. And then the maximum is on the sides. And here it's going up to 4 times the peak frequency. And that difference between the wind direction and the angle of that. So here at 4 times peak frequency, maybe up to 60 degrees. So which makes like 120 degrees for the distance between 2 peaks. And what we found with video data is if you actually go to even higher frequencies, like 5 or 6 times the frequency, this angle will grow even to 75 degrees. So it's almost opposite directions the waves are traveling at. So this is what we find in short fetch, young seas, and it was found before by Longo-Griso and some others. Our wave models, we still have a problem in getting this shape of the spectrum. So this is what I want to show you, that the wave models, they're doing good job these days for getting the peak spectrum, the energy, the mean direction, but the directional distribution is still doesn't quite look like this. So maybe it will be a bit flat, but in order to get this trough here between the two directions, you really have to update the parameterizations and do some things. And so there's still some research going on that. It's still not solved, and I still haven't seen any wave model that does this spectral shape properly, especially the ratio between the minimum here and the maximum there. And this is another illustration of the spectrum. So now it's just contours of energy as a function of wave number instead of frequency, and then directions. And so you can see here that minus 90 degrees and plus 90 degrees, that would be opposite directions compared to the wind in the middle, and the maxima are maybe at 70 degrees instead of 90. So it's really a broad direction distribution at high frequencies. Now, most people don't care about high frequencies because there's little energy there, right? And so most people really care about what's going on here at the peak. But if you're doing remote sensing, this stuff is actually very important. And it turns out also that these waves are actually the short waves are the one that define the roughness. And the wind stress, how the strength of the momentum flux between the atmosphere and the ocean depends a lot on the short waves. And so there's still some things to be done here, and that's particularly relevant for things like storm surges. So we know that there's a dependency on the wind stress on the sea state. It's not just a function of the wind speed. And we're still having some issues in having the proper shape of the wave spectrum and then the proper momentum fluxes that go into the wave spectrum. All right, so that was WINT-T, but now I just want to point out that the ocean is not about WINT-T. Even in the Mediterranean, sometimes you have a bit of 12. And of course, you're looking at the Pacific. This is a typical case in the Pacific, in which you have this directional spectrum. So the colors are the energy. In my plot, I usually put direction in direction from which the waves come. So you have the choice of two conventions. Either you put direction to or direction from. For some historical reason, people that work on coastal stuff, they tend to look at the waves where from they're coming. People that work offshore, they will look at waves to. So just, let you know I'm working conventions direction from, okay? And the range here is frequency, so 0 at the center corresponds to 0 frequencies of very long waves, and as you go outside, the frequency is getting higher, which means the waves are getting shorter, right? Because 0.3 hertz is 3 seconds, and of course 0.1 is 10 seconds. These are long periods and then long wavelengths. So here you have the WINT-T at high frequency here, and you have 12s, number 1 and 2 here, which correspond to waves coming from storms very far away. This example is from Hawaii, the NDVC buoy number 51001. And essentially, this is a storm from the Gulf of Alaska, 3,000 kilometers away, maybe 4 or 5 days before. That's a storm north of Japan, again, 4 or 5 days before, and the swell from that storm is reaching Hawaii, and you see these very long waves. And so if you look at the 1D spectrum, the frequency spectrum, you have this very narrow peak for this swell number 2 here. And actually, there's more energy in this second swell here. So this one is 2 meters, this one is 1.7 meter height. Okay, and then you have the WINT-T with 1.6 meter wave height. And yeah, I know, yeah, so that's, well, I have to show. So we'll just make a break after that. So most of the time we'll be working with a 2D spectrum, and for practical reasons, because this is how we process the buoy, it will be often mostly spectrum as a function of frequency and direction. You can go from frequency and direction to wave numbers kx and ky, which is a simple transformation of the coordinates. You have Jacobian to go from kx, ky to f and theta. The 2D spectrum gives you the full statistics of the full 4D wave field. So these 2 dimensions actually contain a lot of things, and they contain everything if you assume that the waves are linear and rotational. And one thing I didn't mention also is that this wave field is homogeneous in space. That's how you can go from space to time. Otherwise, you have some issues. And these hypotheses, linear and rotational, they hold very well, and homogeneous, well, not all the time, because you have depth gradients and current gradients, so you have to be a bit careful if you want to make a kx, ky spectrum. But what I want also to point out is that there's actually very few measurements of the full 2D spectrum. So what we're computing in our model, which is this full 2D spectrum, we actually have very few data to really validate it completely. And so most of the measurements are really 1.5 dimension spectrum, which is these frequency spectrum, so that's 1 dimension, but then you will have these 5 parameters at each frequencies from which we need to cook up a spectrum by inventing some things, but this is really not the full measurement of the spectrum. And yes, so you can use linear wave theory to go from the 2D spectrum to anything you like, the pressure, the elevation, the slopes, and so forth. Of course, this is only if linear things dominate your data. And sometimes you can, I was showing with this Jensen thing and the canonical transformation, you can actually also compute the nonlinear corrections from the spectrum to get a more realistic statistics of the D-surface of some other properties. So I think that's all I had for this one. And so if you have any questions, if you want to take a break,